A team ships a 70 billion assistant. Latency in staging 1.4 seconds per token. A 200 token reply takes 5 minutes. Users leave before the first sentence finishes. They try quantization. Memory drops, walk log barely moves. They add GPUs. Cost triples, latency halves at best. Then speculative decoding. 1.4 seconds drops to under half a second. Same model, same output, zero quality loss. How is that possible? It starts with why big models are slow. Models generate autoregressively, one token at a time, each depending on all the previous ones. And every new token needs a full forward pass through the entire model. Why is that pass so expensive? For a 70 billion model in half precision, it reads 140 gigabytes of weights from memory, every token, and it's strictly sequential. Token 5 can't start until token 4 is done. So the GPU is underutilized. Most of its time is spent waiting for memory, not doing math. The model is memory starved, not compute starved. Now the insight that cracks it open. Checking whether a token is correct is cheaper than choosing it from scratch. Here's why. One forward pass of the big model can score many proposed tokens in parallel because each one's probability depends only on what came before it. Hand it the proposed sequence and it grades them all in a single bashed pass. Same attention, computation it always does, just fed a longer input. Checking K extra tokens costs far less than K sequential passes. So here's the trick. You run two models, a small, fast draft model, and the big, accurate target model you actually want output from. Step 1. Draft. The small model quickly generates a few candidate tokens. Given the cat, it might propose sat on the mat in milliseconds. Step 2. Verify. The target model runs one forward pass over the whole proposed sequence at once, producing the probability it would have assigned at each position. Step 3. Accept or reject. Walk from the first draft token. If the target agrees, it was likely. Accept. The first token it disagrees with triggers a correction and you stop there. Step 4. Repeat. Keep whatever got accepted, append it, and the draft sprints ahead again. So if the draft is right all 4 times, you got 4 tokens for one target pass. If it's wrong on the very first, you still got 1 same as baseline. You can't lose. And here's the part most explanations skip. The output is provably identical to running the target alone, not approximately, exactly. Because accept or reject isn't a heuristic, it's rejection sampling. Accept with probability target over draft, and on rejection, sample from a corrected distribution that guarantees the kept tokens come from exactly the target's distribution. So burn this myth. The draft introduces no approximation. A terrible draft just gives you a speed up of 1. It can never produce a wrong answer. What drives the speed up? The acceptance rate, the fraction of draft tokens accepted. The tokens you net per target pass are roughly K times that rate plus 1. 4 draft tokens at 80% acceptance nets about 4.2 per pass. Real systems land at 2 to 3 times faster after overhead. And acceptance depends on the match. A draft distilled from the target accepts beautifully. Predictable text, code, boilerplate accepts higher than open-ended creative writing, which is where it fails too. Pair a general draft with a specialized medical target and acceptance collapses. Now every round costs 2 passes for 1 token. Slower than baseline. There's a family of refinements. Medusa bolts extra prediction heads onto the target so one model self-drafts. Engram drafts mine the context for repeated patterns, 0 new parameters. And Eagle, the current default in many stacks, drafts at the hidden feature level, pushing acceptance even higher. But the core idea never changes and it's gorgeous. Let a fast model sprint ahead and guess. Let the slow model check every guess in one shot. Pay full price only when the guess is wrong. Same exact output 2 to 3 times the speed.